just want to point out, I got this off the web, right? It's clip art, right? Which just shows that quantum information has reached a milestone, that there's a clip art representation of a quantum computer. So I'm not going to talk about the details, the technical aspects of how this works, but I just will say that, that we have reached that milestone at least. But again, the promise is still there. We still believe that if you can make a quantum computer, then there are certain tasks that can be sped up exponentially, which is really amazing because computer science says, well, it doesn't matter whether you have a Mac or a PC or one processor or another processor. They're all going to basically take the same amount of time up to an overall numerical processing speed factor. But quantum computers can shortcut through some really important problems. One of them is this factorization, which basically would completely disrupt the internet, the ability to transmit information without having somebody be able to read it. But I would say maybe an even more important application is the efficient solution of the time-dependent Schrödinger equation. Right? You could argue that the Schrödinger equation is the most important equation in physics. Maybe you all have your favorites, but this is mine. But really, Nobel Prizes have been given simply for coming up with good approximations to the Schrödinger equation.
Chemistry.
Right? So it's really, this is really the basis. If you can efficiently solve that equation, there's an enormous amount, I think, that we could learn from quantum computer science and so forth. So I'm very interested in spin-based quantum computing, and one of the challenges is that, okay, you've got two electrons, and you want them to talk to each other and so forth. Well, how are you going to hold them? Well, one way to hold them is to confine them in let's say, a semiconductor, and then to put gates and so forth that prevent them from exiting. Just like what is depicted here, this is a scanning electron micrograph, some work done at Delft University, but this is basically a system that can hold two electrons, and they've gotten very, very good at this with gallium arsenide-based structures. So the question is, can you do this with these oxides? Well, we think that we can. We've made some inroads into this. So we actually made a single electron transistor recently. So this is a device that had an island that was 1.5 nanometers in size, connected to 3 leads. And one of the leads would then lead to resonant tunneling between these devices, and between the island and the leads and so forth. We think that this may, in fact, be a building block for other types of quantum devices and spintronic devices as well. So another way in which you can use quantum mechanics is to do something a little bit fuzzier, which is quantum simulation. And here the idea is you have some physical system, maybe interacting electrons. It's very, very complicated. It's hard to solve, even numerically. It may be possible to map that onto a physical system and let quantum mechanics just run free time without worrying about ones and zeros and try to get information about that system. So the idea is that you can start with some general system and perturb it in certain ways. So I'm thinking about taking, again, a blank canvas here, writing on it different patterns. It may be possible to create structures where electrons can reside and hop between islands and so forth, and that system can be mapped onto really intractable physics problems. So this is, of course, goes really back to when Feynman was thinking about how quantum mechanics can be used for computation. So we're very much interested in trying to build one of these kinds of processors to do quantum simulation. So the last thing that I want to talk about is quantum preservation. So I didn't mention this. I've been glossing over a lot of stuff, and you can ask me about afterwards if you'd like, all the things that I've neglected or thrown under the quantum rug. But one of the things that's very, very challenging in quantum computation is that what's called decoherence, or errors that creep in because systems are by necessity coupled to the rest of the universe. And so that coupling makes it difficult to preserve the quantum information, because to preserve the crisp phase differences that you need between states in your system to be able to execute these quantum algorithms. So one of the very really fascinating, I'm not a theorist, but from my point of view, fascinating theoretical developments since the development of quantum computation and the modern framework is the idea of using topology. So I've been saying, well, everything is distinct, right? But in fact, we know topologically that a donut is the same as a coffee cup. So being able to make that identification between them, say donut, coffee cup, somewhere in between, it doesn't matter, that kind of a fault tolerance, if that can be ported into the quantum domain, can be very, very important and a quantum leap forward for quantum computing. So it turns out that there are theoretical proposals, very abstract, but the idea is in fact to use particles called Majorana fermions, which have never been detected in the universe so far. So first you have to get not one but two of those, right? And then you have, or maybe more, and you have to start braiding them. And in fact, it turns out that working in 2 dimensions is not only helpful, but is essential, because it's only in 3 dimensions that you can make knots and braids, right? We know that. But in this case, 2 of the dimensions are space, and 1 of the dimensions is time. So the idea is that by braiding in the space-time diagrams, braiding the trajectories of these Majorana fermions, you can create states which are rich enough and distinct enough to map onto quantum computations. And so this is way, way out there, but in some sense, we are doing particle physics in solid state. We're trying to find new particles and try to do some very fundamental things as well. Okay, so to summarize, I began with talking about this relationship between the sort of universe and your PC, right? Bits and matter, that they're really not a very fundamental distinction between them, and that the laws of physics are really used for processing. So my own interest in oxide nanoelectronics basically was motivated by this, by childhood memories of playing, as well as being able to, trying to search for ways of finding new systems that have these states that can be switched from one to the other on a small scale. And that was really what we were searching for. We stumbled upon it, but in fact, it's a directed search, and we've been very active, and it's sort of taken over a lot of what goes on in my group. So we're very interested in understanding the properties of these new materials, these complex oxides, and their ability to switch at the nanoscale. We think that there may be lots of applications, interesting applications, not only for conventional computation, going beyond Moore's law, or maybe something that would be useful in 10 to 20 years from now, but also maybe something that goes beyond that would be useful for quantum computation, for being able to solve the Schrodinger equation and be able to read somebody's email. That kind of thing, I think, would have enormous impact. Okay, probably the former would be more of an impact than the latter. But the point is that I think that there is an interesting system, both from a classical and quantum point of view, and as well as from fundamental areas as well. So I would like to acknowledge many people who worked with me, beginning with Joachim Manhart from the University of Augsburg, who introduced me to this physical system, but other collaborators as well from Berkeley, Wisconsin, and from my own group, Cheng Sen. She's the one actually, she was a graduate student with me, and then stayed on as a postdoc, now working at IBM. And she was really instrumental in making this work for the first time. Well, thank you for your attention.
A few folks may need to leave, but time for a quick question or two. Yes?
Some of what you were doing required a water cycle, and so it wouldn't work in the desert, I guess. But once you're in
Okay, so the question was speed. Well, we do know that we can actually, let's say a millisecond, we can, basically a millisecond pulse is all that's needed to change on a small scale. I wouldn't want to use it as a logic gate, because as you pointed out correctly, that it's too slow. However, for the construction maybe of circuitry, and then coupled with the fact that you can do these things in parallel, I think it is possible to use it either for storage, because again, it gets multiplied by the number of probes. So we're just working with one, but you know, you can imagine having a million of them. It's not science fiction. There are researchers who are working with those. So then it becomes a little bit faster.
Yes?
Is it absolutely clear that low states are stable forever? I mean, do you know that they're stable for years and years?
Okay, so yes, that was one of the things I glossed over, was how stable is this writing process. So we do this experiment in room temperature, and when we write the structures, they are stable for about a day in air. If we remove water vapor by pumping out the system and or cooling the system down to low temperatures, then they do seem to be stable indefinitely. So control over basically the relative humidity is important for the longer term stability of these structures.
Okay, I think we should wind this up and thank both. Down if you have questions for either speaker.